So I was asked you a little brief how I got to the position I'm at because it's the early career workshop. I'm a little different than probably what you'll see with most professors. I went to University of South Florida for my bachelor's degree, got a degree in mechanical engineering. I did an internship as an undergrad, learned very quickly I did not like mechanical engineering. So I did not do the professional engineering course. And my first job out of school was still in engineering, but it was in a very new technology. Now I'll start dating myself here. And that was digital music. So I worked for Warner Brothers on the very first all-digital road show, Bugs Bunny on Tour. So I did the sound and lighting programming for that tour. So when you go to a conference, you see the lights spin and move. So I work on those when they first come out. Dat tape. So that was my first gig out of school. Made twice as much money as everybody else I went to school with in mechanical engineering. So, but like all things in the entertainment industry, did not last very long. So then I was looking for another new job. And just by circumstance, I answered an ad at a reprographics house. These are people who make blueprints. Everybody know what a blueprint is? The architecture. And they had just got the first digital color copier in the Southeast US. And they needed somebody who understood DOS, knew how to print out from AutoCAD. Engineering could do that. So I went in, convinced them I knew all about this equipment and I could make it run. No clue. I went to the library real quick, got some books, studied up all the night before, went to the job, made that place sing and dance. So I was, again, very first involved with digital technology for printing. So from that job, I went on to work for a local distributor, and from there, within 5 years, I was working for the international manufacturer, so Ricoh Corporation. And I was the Southeast digital color sales manager. So I had a nice cushy 6-figure job. My best friend was Uncle Rico. That was my credit card, my corporate expense account. So I loved Uncle Rico. And it was a great job. You know, I was in when that technology is new. I know some of you are thinking, wow, how has it been around for a while? It wasn't always around, believe it or not. So that first machine ran on DOS. You had to type in code to get the color print to come out, and it took about an hour to get an 8.5 by 11. And we thought it was great. So those were the first systems. But going through that, eventually the color revolution happened, and now everybody has color printers, and Y2K didn't happen, and the copier industry kind of started to go downhill. And what's happening is the digital revolution is everybody's switching from using books to doing electronics and using email instead of printing. So at this point, I started thinking about what am I going to do for the rest of my life, because this industry is not going to stick around until I'm 65. So I started to think, what things I really enjoy doing? And I had an opportunity with Ricoh Corporation. They told me I had to they redrew the district, so my district went away. So I went down a step. They said, well, since you're taking a pay cut and a step down in responsibility, why don't you go back to school? We'll pay for it. I'm like, great. So you want me to get my MBA? You don't have to. I'm like, what? Take whatever you want. I'm like, can I take oceanography? They're like, yeah, we'll pay for it. We're doing it. So I started taking online classes, working full-time, traveling all over the country and the world. So we would do classroom discussions online, and my classmates would ask, Kristine, where are you at today? And I'm like, I'm in Bermuda, I'm in Las Vegas. So it was really fun. But eventually, the job markets turn around. Ricoh was doing another restructuring. So I had the choice of making my territory would be the whole U.S. and working for a boss that I liked, or I could stay in Florida, work for a guy I couldn't stand. So I had to make a decision. So I had been taking classes. I took a 4-week ecology class at night. I talked to my professor. He said, in high school, I was a smart girl. I said, I always thought about going to graduate school, being an oceanographer. That's what I really love to do. But I don't know if I can do it. At this time, I'm about 32, 34 years old. So she said, take a class, write a term paper for 5 minutes a semester. So I wrote my paper, turned it in. She gives it back to me at the end of the semester with an envelope, and she wrote on it, see me after class. And I'm thinking, oh my gosh, I bombed this term paper, it's awful. So I went to see her, and she said, this is the best term paper I've ever had a student turn in. You haven't taken this. So she asked me to go see Professor down the hall. He became my PhD advisor. So my meeting where I had to tell my boss who I was going to work for, we went to a really nice steak restaurant in Atlanta, ordered a really expensive bottle of wine, most expensive steak on the menu. He's like, so what did you decide? I said, you know what, I have a third option. He goes, third option? So that's it. I'm going to go back to school and get my PhD. So I quit on the spot, went back to school, got my PhD, went from a 6-figure job to a student stipend. So basically, an order of magnitude decrease down. But you know, and it's weird to think about that. So that was 2003, August of 2003. I decided to go to grad school. It was a big decision. You know, I had an expensive house, expensive cars. I kind of paid for all of this. But looking back now, it was amazing how much I learned in such a very short amount of time. And the difference is now I love what I do. You know, it's like I went from grad school right into a postdoc. The day I defended my dissertation, I conducted my first interview with policy. It was the morning of my defense. My interview, to give my defense, went to AGU a couple of weeks later. While I'm at AGU, presenting my first talk ever to a large group, got the offer from LSU. So it happened really fast for me. And I'm glad it did. And I like LSU, I like what I do. So that's my personal story that I've wanted to share with you. It's because, especially for young folks, you don't have to make decisions for the rest of your life now. You can change them down the road. It's okay. You can do it. You know, in your mid-30s, 40s, 50s. If you want to go back to school, you can do it. So yeah, you can do it. Is it tough? Yeah. Young folks are going to make you run around really fast. But anyway, so I mentioned that I like scuba diving. So this is probably one of my favorite places to scuba dive. This is Dry Tortugas National Park. It's the westernmost Florida key. Most people only go as far as Key West. Anybody go to Key West? Okay. Anybody go to Dry Tortugas? Yes, awesome. So it's a 3-hour boat ride from Key West. And it's not cheap, it's about $150 now. You take one ferry goes out a day. You take a seaplane, that's about $500 for the ride. This is a really beautiful place to go. The reefs here are still alive. The shot I'm showing here of the island in the background, that's Loggerhead Key. This is part of the Marine Reserve. So in that part of the park, I cannot go in and collect corals. That's because we want to keep those corals alive for as long as possible. The other thing I'll point out is you'll see this like dark object over here to the right on both slides. You guys see that? That's Fort Jefferson. So that was a Civil War era brick fort, the largest one the U.S. ever built. Dry Tortugas has been occupied by humans, Europeans mostly, for a very long time, since the Spanish. Fort Jefferson is a really cool place to go. And one of the reasons why I use this site to do my research is because there's instrumental temperature records and salinity records out there. The fort surgeon actually made daily water and air temperature measurements from 1878 to 1990. So I've got real daily observations. I can use my daily conversation. So this is a really special place. If you ever get a chance to go. And that is my public service announcement for National Park Service. Okay. So just a little overview why I do what I do. So hopefully you guys are familiar with this diagram. So this is the global average temperatures showing the global warming trend over the 20th century. And that's all based on our instrumental records. But normally you'll see this diagram. It's called the hockey stick. Okay? This was originally published back in 1996 by Michael Mann. And what he did was take a lot of paleoclimate records and compile those to look at what northern hemisphere temperatures have been doing for the past 1,000 years. And by looking at this graph, you can see that temperatures we're experiencing at the end of the 20th 21st century were warmer than anything we've seen in the prior 1,000 years. So at this point, good skeptics should be asking, well, where did that data come from? Because 1,000 years ago, people weren't making observations with thermometers. So where is this coming from? And that's where paleoclimate comes in. Another question a lot of skeptics will ask is, how do we know CO2 has changed in the atmosphere? So again, same hockey stick diagram, but now I'm showing it with CO2. So CO2, we can measure, that started with Mauna Loa, with the Keeling observations of the Keeling curve, but how do we know what CO2 was going back 1,000 years? So this is where paleoclimate comes in. So just a little bit on the basis of paleoclimatology. We work on the principle borrowed from geology, and that is that the present is the key to the past. But for paleoclimate, we're going to turn this on its head. And what we're going to say is the past is the key to the present and to the future. So, and this is really important because what we want to do is find similar intervals in the past that could be analogs for future climate change. If we can understand what natural climate variability is in those intervals, that can tell us something about what will happen in the future. So that's a lot of the things paleoclimatologists do. So how do we do this? So first off, you need to go in and set up a way to tell time. Now, I'll put this caveat in. This morning you guys had a great talk about paleoclimatology out at Lubbock Lake. So that would be a type of paleoclimatology I call low resolution. What I do is high resolution. So we're going to be looking at types of reconstructions where we can get into weekly resolution, monthly resolution, annual resolution with some of these proxies. When you're looking at sediments and radiocarbon dates, you can't get to that kind of resolution. So it's still paleoclimate, just two different varieties. So for high resolution, even with low resolution, these things that you need still apply, but we're going to apply them in different ways. So first off is you need to be able to establish time. So how do we do that? So they talked about radiocarbon dating this morning. Okay? So we're going to use different ways to tell time in the proxy records I'm going to show you. The other thing you want is a proxy that is going to be sensitive to some climate variable. So instead of using a thermometer, we're going to use something that happened in the environment. So you think about it. What's a thermometer? How does it work? Does it just magically feel how many electrons are pumping into it? No. It's using a proxy. If you have a mercury thermometer, it's using mercury, or alcohol, you have an alcohol thermometer, right? And they're using the properties of those liquids to see what the thermal adjustments are. Okay? So that's a proxy. I would argue that's a proxy. So we're going to do the same thing by looking at things that change due to how the environment changes. Now, resolution is different from chronology. Chronology is how we tell time going back into the past. Resolution is what my time step is for each of my observations. Okay? So they're two different things. And then probably the most important part of what we do is understanding the limitations. So just like if you guys were to go out and make some temperature observations, right? So what would you do with your thermometer? You look at it and you try to figure out what the accuracy and precision is, right? Is my thermometer calibrated? You know, if it doesn't match up to some standard, we may need to get our thermometer fixed and do a correction. And then figure out what's the smallest measurement I can make with that thermometer. So that's understanding the limitations. So that's a lot of what paleoclimatologists do. So what I'm going to do is kind of give you an overview of different types of proxies, and then I'm going to talk to you about one of my newest studies and what we're doing because I'm using all kinds of proxies. So this is from the NOAA Paleoclimatology website, and this is where a lot of the high-resolution records get archived. So you have tree ring records, that hockey stick reconstruction, most of that is tree ring. So the other proxy that's used quite a bit is ice cores. So a lot of what we know as CO2 all comes from the ice cores. So other proxies we use a lot of is marine sediments. We also use freshwater sediments. Okay? So there's things that are buried in those sediments that we can use as proxies of past climate. So there's other things like historical documents, fires, cave records. Cave records is the new sexy paleoclimate. Everybody So they talked a little bit about pollen this morning. So there's lots of different paleoclimate proxies. So I'm going to go to tree rings just because they're the first for the high resolution proxies. They've been doing it for a long time. So Douglas started this back at the University of Arizona back in the early 20th century, looking for connections between sunspots and tree rings. So how does dendrochronology work? So we have our increment board, we go out to a tree, we take a core out of this tree, and if you look at it, you'll see all those rings. So if you ever look at a tree that's been cut down, you've probably seen the rings. So these rings vary in their width, and they vary for different types of reasons. So why do tree rings vary?
Moisture availability.
Moisture availability, good. Anybody else?
Different seasons.
Different seasons, yes, that's why there's rings.
Growing season length.
Growing season length.
Drought.
Drought. Ooh, jump on it. Sorry. Okay. Is that right? That's right. Okay. So temperature. So if you go to a tree line, or you go close to the Arctic Circle, trees there are very sensitive to temperature. If you go to drought regions, trees are going to be very sensitive to drought. So if we were to go out and plant some trees here above it, what do you think they would be sensitive to here?
Drought.
Drought.
Mm-hmm.
Right. So with tree rings, we can look at those rings, and again, it's different locations tell us different things, different species tell us different things. It gets interesting. I'm not going to say it gets complicated. It gets interesting. So the basis of dendrochronology or tree ring studies is looking at the ring width. And you'll notice looking at this diagram, you'll almost see like there's some years that are really wide and some years that are really close. So it almost becomes a barcode. And what dendrochronologists can do is look at that barcode from one tree to the next. So everybody growing in the same area and match up those barcodes. Because it's environmental forcing, everybody's feeling the same environment. If it's biological, that's different. So we want to find that same environmental forcing. So by lining up these barcodes of the trees, we can assign a master chronology. And using this technique, we can establish lots of trees in an area, how they were all growing. Now what's neat is we can do absolute dating with this method. So if we got live trees, we know when we cord the tree. But let's say I got some dead wood. And I want to figure out when that tree died. Okay? So I can take its barcode, line it up with all my live trees, and find where it matches. And I can date that dead wood. Or if we go out to an archaeological site and they're using timber in it, we can take a sample of that timber, line it up to our master chronology for that region, and we can date that timber when it was taken down and used in reconstruction. So dendrochronology has a lot of powerful uses. Notice that pretty much everybody who's doing high resolution paleoclimatology is using this type of principle in their research. So any questions on this part so far?
How far we can move?
The longest tree reconstruction is actually the radiocarbon calibration curve that is at 10,000 years. So most areas, a couple thousand years. The American Southwest is where they really push it back, and that's also the really old tree belt. So in the Gulf Coast, we're about 2,000 years. So it varies by location. Good question. Okay, so while we're talking about locations, so where do we have tree ring reconstructions? So again, looking at this map, some things should jump out at you. One, a lot of tree ring reconstructions are done where? What type of geography? Right, mid-latitudes, high latitudes. What else?
North of the equator.
North of the equator. So North America, Europe, there's lots of scientists. So how about down in South America? Why just in that area of South America? Why not the Amazon rainforest? There's lots of trees there. Right, no seasons. We don't put down bands. So, or multiple bands a year. So they're more precipitation driven. So, but why go to South America? Why that location? Mm-hmm. What's happening there?
Like high altitude.
Yes, high altitude. So in the mountain ranges, same thing. You come over here, just north of India, going into Nepal. What's there? Big mountains. So these are all trees growing up there at the tree line. So they're sensitive to temperature.
And how come there are no neon?
Sorry?
So it's actually light.
Yeah. There's mountains there, right? So I guess we need to do the clouds to go there and learn. It's the same thing in Africa. You'll notice there's not a lot in Africa, and part of the reason is because people haven't gone there and do the work yet. And in the rainforest in Africa, again, it has the same problem as the South American rainforest. So you'll notice when we get the maritime continent region, the Arso, you get to go up to the high latitude or high elevations. It's starting to happen. There's ways to do it, and it's all new work that's being developed.
Is this a database?
Yes, this is out of the NOAA Paleoclimatology database. So this is, as of Monday, all the tree reconstructions done in the archive. It's not all the ones in the whole wide world, because I didn't contribute to NOAA, but a lot of research. So, it's Australia, Palo, research. There is a rainforest over here on this side. But it's starting to happen. So now, looking at this diagram, you'll notice we have lots of tree rings in some places, but in the tropics, we don't have a whole lot of reconstruction. And I might be biased, but the tropics are really important because that's where all the energy's coming in, right? So we need to know what's going on in the tropics. Tree rings are not going to help us understand what's happening in the tropics. So we need to find an archive that works in the tropics. And that's where corals come in. So this is a proxy I do most of my work with. The picture over on your left, that is not a rock. That is actually a coral. So that's a massive coral colony. In the Pacific Ocean, they can grow as high as 4 meters tall and be up to 800 years old. They're huge. Okay? So most people think of coral as these little pretty branching things. So those are maybe only 30, 40 years old. These guys live for a long time. So what we do for coral-based paleoclimatology is we go out and work with these massive corals. So we scuba dive in the middle of that colony, where it should be the fastest growth. We're going to take a core out of the middle of it. And that's what you see over on the right. That's actually the cores from dry tortugas. The top of the coral is what's alive, and everything below it is dead. So as the coral grows, it puts down the skeleton below it. It actually goes on the top of the skeleton. So this builds a chronology as we go back through time. So I'll walk you through how we do our reconstruction. So we've got a little coral, that one's dry tortugas. Notice a lot smaller in the Atlantic. So that guy was about this high. And it was about 150 years old. If we take those cores and cut a slab out of them and take an X-ray of it, because it's skeleton, it's the coral skeleton, it has density variations in it. So if we look at this, what we see is the coral actually puts down bands or rings just like a tree every year. So if we know the age at the top when that coral was collected, we can count those bands from back in time to establish the year. So that's how we do our chronology. With massive corals, we have different growth rates. It varies by species, varies by location. So once we figure out our chronology in the coral, what we do now is some geochemistry. So we use this fancy drill system that I have in my lab. We go into the coral skeleton and we remove about enough material to do our chemical analysis. So an equivalent of what I need to do a temperature reconstruction, about 5 grains of sand. So that's what I'm removing out of the skeleton. It's not a lot of material. Once I get back that small sample, I can then run that through one of my instruments that measures the chemistry of that skeleton when it was growing at that particular time. What we do here is a little reverse chemistry. So remember from chemistry lab, we did Chem 101, you always did things at STP, so standard temperature and pressure. You assume you're at sea level pressure. So in that chemical reaction, we have a certain outcome based on that temperature and pressure. So we're just doing the opposite with our geochemistry here. So we look and see what that resultant is, and we know the thermal properties of that particular compound we're looking at, and from that we can back out what the temperature was when that skeleton was formed. So using our micromill, we can do high resolution reconstruction up to weekly. Most of what I do in my lab is monthly, because we don't really. So it depends on the question you're looking at. So if I'm doing this, we can go in and reconstruct really long records of what happened in the past. So I'm going to show you my reconstruction of dry through this. But before I show you the reconstruction, you need to understand why it's important. The reason for that is the Gulf of Mexico and the Caribbean is the moisture source for a lot of the precipitation we get in Central America and North America. So a lot of the rain you hear in Lubbock, guess where it's coming from? Gulf of Mexico and the Caribbean. So if we understand what's happening with temperature in the Caribbean, that tells us something about moisture flux. And we can connect that back to drought that we see on land. So we want to know what's happening with ocean temperatures as we go back in time. And there's some marine sediment core records that have gone back to the Little Ice Age, which was just about 150 years ago. And they say the Gulf of Mexico was 2 to 3 degrees colder during the Little Ice Age. Now 2 to 3 degrees colder is how cold we think the Gulf of Mexico was during the last glacial maximum. So this is really cold. And that means a decreased moisture flux in North America. Now the interesting thing is, if you look at the diagram to your right, this is a climate model study for the Gulf of Mexico. So what's going to happen with global warming? So as we go into a warmer future, what the models are telling us is that the Gulf Stream and Atlantic Meridional overturning circulation slows down. When this happens, the Gulf of Mexico gets cold. That's that blue box one. So this is kind of a paradox. It gets hot, Gulf of Mexico cools. It gets cold, Gulf of Mexico cools. Okay? So let's see if we can look at this question in more detail. So I'm going to kind of jump to the end and show you the full reconstruction. So this is my reconstruction of the dry tortugas. It was made with 3 different coral cores. So two of the corals were collected alive, one of the corals was collected dead. We did not do uranium carbon dating, or we did uranium carbon dating, we did uranium thorium dating. That's because I can get really precise measurements down to plus or minus a couple of years with uranium thorium. So I have a cross-dating chronology, multiple corals, and we can go in and look at what climate did in the past. I'm going to use my historical temperature records from Fort Jefferson to do my calibration. So this is a pretty good reconstruction. The blue line there is an air temperature record from Key West. And you'll notice the reconstruction in black tracks that air temperature record through these flows. There's 100 kilometers between these two locations. And the gray that you see around the reconstruction, that's my error bars. So that's how certain I am. As you go back into the record, you get to just one coral record, you know, the error bars get bigger. When I have 3 corals, the error bars get smaller. Okay? It's the same thing in that hockey stick reconstruction at the very beginning. So by looking at this, we can go in and start to ask questions about, okay, what happened in the past? So let's look at the Little Ice Age. Little Ice Age is really interesting because I do have time intervals where it gets almost 2 degrees colder. But you'll notice there in the 1750s, it's almost as warm as the late 20th century. There's quite a bit of variability during the Little Ice Age. Now the other thing that's interesting is Little Ice Age, a lot of what the causes of the Little Ice Age is tied back to the number of sunspots. So the Dalton minimum is a time period when there's very little sunspots. If you look at this reconstruction, you'll see that it's actually colder for the Dalton minimum. During the Dalton minimum, it's warming. And it's not our coldest period. Okay? So for this particular site, it does not look like sunspots is driving what we're seeing with the Little Ice Age cooling, and we don't see constant cooling. It gets warmer. So this particular site is really interesting because dry tortugas is right there at the edge of where the loop current leaves the Gulf of Mexico and comes back to this site. The loop current is leaving right here, and And as it exits into the Strait of Florida, it goes right past right through it. Goes around Florida, becomes the Gulf Stream. So what we're seeing is that formation of the Gulf Stream in the Gulf of Mexico. And it's quite variable. There's no AMO in this structure. So again, it's one of those things that makes it really interesting what we do. Everybody said you should see AMO. I sliced it and diced it 5 different ways. It's not okay. Atlantic longitudinal oscillation. So that is the sea surface temperatures in the North Atlantic on 20 to 30 degree time scales, which is warm or warmer during the cold. And some folks have tied that to how many hurricanes we have in the Atlantic. So right after Hurricane Katrina, everybody talked about where we can expect 21 years of warm hurricanes. That's what they were talking about. Yes.
What caused the gap in the usability of these cores? So it appears there's that space between, am I reading that right? The number of coral cores, the
Right.
bar at the bottom.
Mm-hmm.
Why would a third core only be useful for a shortened period of time if the gap in between?
Good question. So,
core or something.
Right. I had, so my cores were all the same. So my big one was 200 years, but I had a shorter one that was only 120 years. So one ended, then my dead coral actually overlapped with that live coral by about 10 years. So this is that overlap period between my dead coral and my shorter coral. So that's why. But good question. Any other questions? Kind of neat, huh? The thought is whenever because where does our energy come from? It comes from the sun. Okay, so if you have sunspot variability, you actually get a change in the amount of energy that's coming from the sun. It's less than 1/10%, but a lot of people have suggested that sunspots are driving what we're seeing with natural variability. Okay? And again, with sunspots, it doesn't look like it's influencing the whole Earth. It's sensitive in particular regions, but not everywhere. So that's one of those things, like going back to Douglas, the guy who started the tree rings. He was looking for sunspots driving climate. So again, it's one of those people trying to understand what's happening with climate. So sunspots is one of those things we go look at first. But I think now pretty much the consensus is sunspots is not driving climate, at least not on huge global scales or hemispheric scales. Okay. Alright, so now I'll show you something new. Nobody else has seen this baby yet. So we have, I was just showing you live corals. We can also work with fossil corals. So one of the new projects I'm working on for my PhD students is looking at fossil corals that were collected in the Dominican Republic. We have uranium, thorium dated these corals, and they're 128,000 years old. So this time period is called the last interglacial. This was the last time the Earth was as warm as it is today. And what's interesting about the last interglacial, so we have ice ages. Okay? During this particular period, sea level was 6 meters higher than it is today. Okay? That's natural kind of variability. Okay? So one of the things we're doing is looking at this particular coral. So it's 75 years long. And we're going to look at what the last interglacial was like in the Caribbean. So this is a project that we're working on. The data over on the right is the modern coral data. The one on the left is from the last interglacial. And what we're seeing so far, it looks like that variability is about the same as what we see in the modern versus last interglacial. There's one little point there, it's a little higher. This one right here, which is kind of interesting. But again, it's a short interval. We haven't run all the modern data yet. But this is one of the projects we're working on, is looking at those analogs in the past to inform us about future climate change. All right, so another really important archive is ice cores. I do not work on ice cores. I look at a lot of ice core data. So the way ice cores work is they also can have layers in them, just like trees, just like corals. So a lot of times what those layers are from is you get deposition in the winter, snow. In the summertime, it gets windy, you get a little dust layer. This image you're looking at here, this is the Calcaya Glacier down in South America, and it has little dust layers in it. And that's why you see those bands. Okay? Now, the way an ice core works is pretty neat. So you get snow that deposits during the winter. And over time, that snow is going to get compacted and become ice. Now, as that snow becomes compacted, it's still in connection with the atmosphere above. Eventually, it'll get to a point where it's so compacted, it's no longer connected to the atmosphere. It's the same. Here's that compaction. So what happens down here at the bottom is you get little time capsules of atmospheric air embedded in the ice. This is how we know CO2 has changed, because we're actually measuring the CO2 in little time capsules of ice cores to tell us what the atmosphere was like in the past. The ice cores give us some really interesting processes. And here's what an ice core looks like. So this is one from Greenland, and you can see the layers in the ice core. Count the layers, you can tell what year it is as you go back into the past. So where do we get a lot of our ice core records? Obviously places where there's lots of ice. So Greenland and Antarctica are the two big ones. So last night during our trivia night, we had this question. So how, if all of Greenland was to melt, how much sea level rise would that be? About 6 meters, or 20 feet. If all of Antarctica was to melt, it's about 60 meters of sea level rise. Okay, so not only do ice cores tell us something about CO2 in the atmosphere, we can look at the chemistry of the ice to figure out what temperature is, but we can also figure out what sea level was like in the past. Because to build these big ice sheets, you have to take water out of the ocean, store it on land. So lots of things we can tell with ice cores. I would say ice cores have probably taken over as probably one of the most useful paleoproxies we have. This is a famous reconstruction from ice core. Ice core existence of Vostok ice core record. For those of you who don't know where Vostok is, it's down in Antarctica. It's that yellow star. You guys see it? Have you guys heard of Vostok? So it's been in the news lately for something. Anybody remember? So under the location where they're drilling the ice cores, we found a lake. Lake Vostok. So this lake has been sealed off from the atmosphere for millions of years. So 10 years ago, they stopped ice coring operations when they figured out there was a lake there. So scientists and engineers have been spending a lot of time trying to figure out how do we get down to that lake water and sample it without contaminating. Because there could be organisms living in that water that have been sealed off. So we want to study that. Okay? Paleoclimatologists, we want to go right through that lake down to the sediments at the bottom. We want to see what's in those sediments. So again, this is Antarctica. It's a tough place to work. They would go down there in the summer. I think there was in the news last week, NSF had to medevac out a researcher. They got sick. But it's a pretty tough place to go work. But these types of records tell us a lot about the past. So this morning, when we were over at Lubbock Lake, we were talking about Younger Dryas. Right, say what Younger Dryas is. Younger Dryas, actually, it's Vostok, I can't see it.
You're good at what you do.
It's not there. Younger Dryas, what didn't happen in that model. But anywho, okay, so here's today, 10,000 years over here on the left. So the top data, that's carbon dioxide. So that's our little air bubbles. We can go and measure what happened. What CO2 is like in the atmosphere. We also have methane. We can also see what methane was like in the atmosphere going back over 40,000 years ago. Temperature we get from the ice by looking at the isotopes. So isotopes is just the ratio of heavy element or the heavy mass of an element versus the light mass. Okay? So by looking at all these different records, we can tell a lot about what happened in the past. What we're looking at here is the ice ages. So here's today, last glacial maximum. This little blip right here. Last interglacial. So my coral from the Dominican Republic, it's going right up there and it's going down. Sea level, this is delta 18 here. Graph B, this is how sea levels change in the past. Because when we take water out of the ocean, it changes the So the last 4 ice ages are in this diagram. So ice cores, pretty interesting topic to work on. Okay, but now let's go back further in time. How do we do that? Problem with ice cores is you have to go to some place once you run out of like Vostok, they run into a lake, can't pour anymore. So how do we go back further in time? This is where marine sediments come in. And this is where marine geologists work with. You guys notice that boat down there at the bottom? What does it look like? It looks like a drilling ship. This ship, 6 months out of the year, is out there looking for oil. 6 months out of the year, NSF rents it, and we go out and do science with it. Exact same technology. The difference is we keep the mud, the oil companies are interested in the ones at the bottom of the hole. But what we see in this mud, or these sediments, is all kinds of organisms that live in the ocean. So I'm showing you this middle panel. That is a phytoplankton that lives in the ocean. It's a foraminifera. That's what it looks like when it's alive. The picture in the upper left is its shell, what it looks like when it's not, when it's dead. This is Globigerina ruber. It's a very common plankton we have in the Gulf of Mexico. So when these organisms are alive, they get eaten, fish eat them, eventually that all the organic material settles down into the bottom of the ocean and gets buried in sediments. So we can go into sediment cores, and in these sediment cores, we can look at different types of organisms that are archived there in the sediments, and we can reconstruct what temperature was like in the past. So over here on the right is some sediment cores. Where you see those white areas, that's telling me that there's lots of things making calcium carbonate. Calcium carbonate's white. These little planktons. Whenever there's lots of organics, you get black areas. Okay? So by going in looking at these sediment cores, we can reconstruct what happened in the past. So with marine sediment cores, we can actually see the ice ages. Not the same detail we saw with the ice cores, because we don't quite have the same resolution that we do with ice cores. But we can see that there's ice ages. And you notice this goes back a little further in time than Vostok. We're going back almost 800,000 years ago. And we can see that there's been more than 4 ice ages. So, and here's, just for comparison, where we can get to with ice cores. So with marine sediments, we can go back even further in time, back 5.5 million years. We can go even further in some locations. So what this bottom graph is showing us is actually coming out of the hothouse Earth into the ice ages. So you see that gradual cooling trend, where you start to see those big swings at the end. So those are the ice ages. So here, that's the cooling into the ice ages. So marine sediments can tell us a lot about past climate. And there's where ice cores come. All right. So we were talking about marine sediment cores and ice cores and how they can tell us something about sea level. There's other ways we can reconstruct sea level. And that's by using my favorite organism, corals. So we're going back to corals for a little bit. So this is actually a coral, a massive coral from Haiti. It was uplifted out of the water during the 2010 earthquake. So this particular coral, you'll notice the top of it looks kind of rugged because it was dead. It was growing right at the surface. So this coral was growing out to the sides. We call these microatolls. Microatolls are really good at tracking sea level. So with these types of corals, we can do earthquake reconstruction. We can go back and see what sea level was like in the past. So if you think about the ice ages, we're building big ice sheets over North America and Asia and Europe. Sea level is going to change. So coral reefs can track this change as we go back and forth in time. So for those of you who know the Florida Keys, right? Guess what the Florida Keys are? It's a coral reef from the last interglacial. So you can actually go to Fossil Coral Reef State Park in the Keys, and you can see some corals that are 125,000 years old. That's because all of the upper Keys is an old coral reef that was submerged. Remember, sea level was 6 meters higher during the last interglacial. So that was the coral reef. Today the coral reef is further offshore. So as sea level continues to rise, that reef is going to move in. Okay. So with corals, we can track where sea level is changing. So with corals, as we're changing through the ice ages, what sea level is, we can go in and start to look at rates of change. But the little diagram here is just showing you what's happening We take water out of the ocean, we put it on land, it changes ocean chemistry. I put a diagram here for those of you who don't know how big these ice sheets were. So the Laurentide ice sheet covered most of North America. So the current estimates is this ice sheet was 2 to 2.5 miles thick. It's as thick as West Antarctica. This is a huge ice sheet. Okay? Most of Europe underwater. I'm sorry, most of Europe is under ice. Large parts of Asia under ice. So sea level is dropping. Enough to drop sea level 125 meters of the last glacial maximum. Okay? So how much was Antarctica and Greenland together for ice sea level change? 66. Okay? We're doing twice that with the ice ages. So if we look at sea level rise, so coming from last glacial maximum down here, 125 meters, and we know this from looking at coral records. And we come through that deglacial up to modern times, so about 10 to 8,000 years ago starts to level off. You look at the rate of sea level rise during the deglacial, we're looking at about 12.5 millimeters per year. That's some quick sea level rise. We're doing that in 10,000 years. So if we look at what's happening with present, so back in the early part of the 20th century, we're about 0.6 millimeters a year. To the late 20th century, that's accelerating to 1.4 millimeters a year. We're currently at 3.3 millimeters a year. We're not quite yet to melting ice sheets. That's a good thing. Okay? If you think about it, that's quick sea level rise, 12.5 millimeters a year. You don't want that to happen. So what happens? What does it look like with sea level rise? We'll come back to my neck of the woods, New Orleans. Okay? Anybody ever been to New Orleans? Awesome city, great food, awesome music. All right, so here's today, 5 feet of sea level rise. Okay? New Orleans today is already below sea level, most of the city. So it doesn't take a whole lot of sea level rise for New Orleans to be underwater. But you'll also notice most of South Louisiana is also underwater. So we're losing a football field a day of our coastal land in Louisiana. Because of global sea level rise, we also have the problem of global subsidence. And that's from removing water and oil from the sediments below Louisiana. And also, we've diverted all that sediment that used to build the delta. We now are sending it out to the bottom of the Gulf of Mexico. We're not building land anymore. So that's just 5 feet, what we're looking at 100 to 300 years into the future. So by 2300, looking at about 12 feet of sea level rise. Lake Pontchartrain's underwater. It's now the Gulf of Mexico. And then going to 25 feet of sea level rise. So 7.6 meters. That's just melting Greenland. Melting Greenland puts most of Louisiana, South Louisiana, underwater. Okay? We haven't even touched Antarctica yet. So what happens if we melt all the ice in Greenland and Antarctica? This is what the Earth would look like. Kind of scary. So I'm going to show you guys a graph of what it looked like in the past. This is what it looked like in the past before we had ice sheets over Antarctica. So LSU would be an underwater campus. Here. So that's what would happen. So again, sea level rise is one of those things that we have to be concerned about. But do we think it's going to get to this point? No, hopefully not. There's a lot of things that will keep Antarctica hopefully mostly frozen. But this is that what if scenario. If we do happen to melt everything. So if you're planning to buy beachfront property in Florida, I would not recommend it. So not even Louisiana. So my house is on top of the Pleistocene Ridge, so that's where sea level is the highest during the ice ages. So I'm good. With this scenario, I'm underwater too. Okay. Sorry?
Looks like you can get some good beachfront property in your Texarkana.
Right? So, yeah, but there's other things you gotta worry with sea level rise. So this is something we're dealing with in Louisiana. So as sea level rises, how do different ecosystems respond to that change? So the map here I'm showing is the wetlands of the U.S. The picture over on the right is what? Can you answer the question?
Cypress?
Bald cypress. So this is one of the iconic tree species we see down in the south. So from Texas all the way to Florida, and then up east. The beautiful trees. Used to be very, very big, too long.
What were the little red dots on the left of the map on the other page? Do you know?
I don't remember.
Okay. I'm just curious.
It might be study sites. This is from the USDA.
Okay.
So, for the trees that I'm interested in is bald cypress, and the map on the left shows you, you're right, shows you today's biogeography of bald cypress. It likes to grow in the subtropics, where we have water, moving water, prefers moving water, and where temperatures don't get really cold in the winter. So, typically up to an elevation of about 50 meters. So the exception is the Mississippi River. You'll notice it goes in quite a bit around the Mississippi River. But most bald cypress we're going to find at lower elevations. So if you haven't seen a bald cypress forest, that's what it looks like. Okay. So what happens with sea level rise? And that is you get saltwater intrusion. So these freshwater wetlands where the bald cypress are growing, they start to get more saltwater. So what happens as you get more and more saltwater in these environments? The trees start to die down at the bottom. And everything else that lives in that ecosystem also shifts. So understanding how these ecosystems may change in the future is one of those things that I'm interested in. So let me show you where my study site is. Does that surprise anybody? John's saying no. So this is my study site for trying to understand what happens to bald cypress with sea level rise. So my study site is 13 miles off the coast of Alabama. It's 60 foot of water. So let's go scuba diving. Well, not yet. So anybody want to take a guess why this is my study site?
Yes.
Well, there's trees, obviously, but
Probably dead trees.
yeah, they're not alive. No. So the reason why this is my study site is because of sea level rise. So if we go back in time, so last glacial maximum 20,000 years ago, as sea level dropped 125 meters, parts of the Gulf Coast that are now underwater were land. You look at Florida, Florida almost doubles in size. Okay? It's kind of a really shallow continental shelf. So same thing with the coast of Louisiana, Mississippi, and Alabama. So when it drops sea level, and now we have land for plants to grow. Okay? So this particular study, I would love to say I was this brilliant scientist who came up with this project. This came out of Facebook. So one of my PhD students, she liked this dive shop. The dive shop posted really interesting stories, so I liked it too. So one day I'm cruising through Facebook. He said, swimming with dinosaurs. I'm like, what? So I started reading the story. So the guy's talking about how there's all these trees at the bottom of the Gulf of Mexico. He said 20 meters of water. So I started getting really excited. So I'm thinking about the sea level curve. So if you look at the sea level curve, this green line at the top, that's 20 meters. Right? So 20 meters about 10,000 years ago. Alright? That's right after the Younger Dryas, megafauna extinction, into the radiocarbon curve. So I started getting really excited. Like, this site's at 20 meters of water. This could be some really interesting science. So I emailed the guy who wrote the story. We started talking to each other. And it's like, yeah, let's go out scuba diving. Hey, so we went out scuba diving. And so did some backup research, like, okay, how did this site have trees? So this is a study that was published back in 2004. This is the Mississippi coast. So this is what scientists think happened since the last glacial maximum to modern. So in the site, the diagram at the top, you've got letters A through the F, and then that matches down here at the bottom. So last glacial maximum, here you see sea levels way off coast. If the delta is forming off the edge of the coast, as sea level starts to rise, these rivers become incised, right? And you're going to have, like today, these freshwater swamps. So the sea level continues to rise, your delta is forming, it keeps moving in. The black star is the study site. So we're thinking, wow, this would be really cool. some wood that's in 20 meters of water. You interested? He said, yes. So went out, scuba dived the site. And just to orient you, before we go underwater, what you're going to see. So this is a bald cypress tree. If I was to go in and cut that tree down, right where that red spot is, you would see something like this. So this is one of those beautiful bald cypress cross sections. So they have all these buttresses on the bottom. So it's very unique with trees. So when you see that shape, you know what that is. Okay, so let's go dive in. What does that look like? They're all over the place. I'm not going to show the whole video. If you guys get the idea of what we see in the water. So that's what we see on the bottom, is these stumps all over the place. So here's a picture of me, my former PhD student diving the site. You can see the bald cypress stump in the background. That's me pouring into the water. So we went out and collected a lot of wood, brought the wood up to the surface, sent a bunch of this wood over to my buddy Tom Gilderson at Lawrence Livermore, who does radiocarbon dating, and waited to get our results back. Like, oh, this is really exciting. Another thing we did is the reporter that I'm working with, he's a mover and shaker in Alabama. He's got friends everywhere. So he convinced the University of Southern Mississippi to go out and map this site for free. This would cost $10,000 to do. So in 2012, I went out with the University of Southern Mississippi and we mapped this site. So this is what it looks like. You've got this hole here at the bottom, and as you go up, it's like this swell, and then either on either side of this, or where all the stumps are. So the fishermen who originally found this site found it in 2004, right after Hurricane Ivan, made landfall in Orange Beach, Alabama. So the hypothesis is that the hurricane moved the sediments to expose these trees. So one of the things we're interested in is how big is this forest, how much of it's still buried, what was this forest like? So back to dating the wood. So after we went out to do geophysical work, sent my samples off to Lawrence Livermore. Tom gives me a call, doesn't email me, he calls me. Hey, Kristine, this is what you said. It's radiocarbon debt. I'm like, excuse me? You mean the analysis didn't work? He's like, no, it worked. There's no carbon 14 in it. And I'm like, what do you mean? It's older than 50,000 years. It's so old, I can't radiocarbon. So at that point, we're going, okay, Bartek 2004 says we should have been fine. Looking at sea level curves, this doesn't make any sense. So I sent them a whole bunch more wood. So the tree that I poured underwater, I sent that core to them to radiocarbon date. It went into a sterilized bag the minute I got on the boat. It was not contaminated. Radiocarbon date. So we've now dated 15 pieces of wood. We're all ready like that. So anyways, we've worked for a long time trying to get funding to work on this project. So we were able to get money from a private foundation. Because I'm working with a reporter, he's published all kinds of stories about this. He's making a documentary. It's gone viral on Live Science twice on us. So we've had people contact us saying, I want to fund you. I'm going to give you money to do this work. Wallace Foundation gave us $25,000 to do this work off of the Live Science story. Bureau of Ocean Energy Management contacted me. So the marine archaeologists said, I'm really interested in why this wood is so well preserved. We're going to give you money to do this research. So taking that money, again, this isn't me writing a proposal, keeping my head up against the wall. People calling me, how are you going to get the money? Which is awesome. So we went out last summer. We did geophysical surveys with some fancy new equipment that can see through the sediments. We want to map where all the trees are. We also took sediment cores. So let's go ride this sediment core down to the bottom of the ocean. So we put a GoPro on it. Again, I'm not going to show you the whole video, but this is the vibrant core. That's how much we're going to drop it off the back of the boat. Showing on my screen. Okay, let me start it over again. I'll turn down the volume. You get the picture of how long this is. Okay, so Gulf of Mexico. For those of you who get seasick, I apologize. So, and this particular day, the water was really clear. Normally off the coast of Alabama, the water's not this clear. We could see the core from the surface when it was sitting down on the bottom. That core raises about 10 feet tall. See it. So it goes down to the bottom. You'll notice when it hits the bottom. So, and then this center core shaft, it vibrates. As it vibrates, it goes down into the sediments. That vibration makes it almost like a knife going through butter. It goes through. So we took 6 sediment cores from different locations. And each time we hit wood. So we back up? Okay. So at the bottom of each of these cores, we hit mud. So these are peaty sediments, typical of what we'd expect in a freshwater swamp. There's wood in the bottom of all of them. We took some of that wood, sent it off to get radiocarbon dating. So this is one of the sediment cores. We've only opened up one core so far. So the first 3 meters of this is all sand. So this was off of the site just a little bit. But as you go down, there's this transition. You can see sand, organics, sand, organics. It'll be a nice big organic layer, more sand again. So this is those changes in sea level. That marine, terrestrial. So we took a sample out of this, sent it off to get radiocarbon dating. This time we sent it to Beta Analytic. We paid money for this one instead of the free stuff. They gave us a good date. So almost 42,000 years old. So again, this is really close to the limits of what radiocarbon dating can do. So this date itself is not publishable. Reviewers will chew us up if we try to publish this date because they know you're really at the limits of what radiocarbon can do. So we went in, had some more samples from the sediment core. So one's up top, we had some organics down at the bottom. Sent those off to Beta Analytic, wrote them a really big check. We were all So again, we're at a site, we know it's ice age, so we're pretty sure we're in marine ice clear stage 3. It could have been from previous glacial. So at least we know we're in the past glacial. So one of the things I'm working on is, I mentioned before that we rain authority dating. So my colleague who does this for me in Taiwan is really good. So he's developing a method for us to do uranium fluorine dating for the wood. This hasn't been done before. So we're doing some innovations, trying to get some things. Uranium fluorine methods, we can go back half a years. So I sent one of my PhD students to Taiwan for a semester to work on this. I've been to Taiwan to work on this. So we're still trying to get this going. So hopefully we'll be able to get a good thing quickly. So we're doing some innovation. And my student who's doing this, he's getting some world-class experience. He's a lucky kid. So other things we're doing, I mentioned tree rings at the beginning. So Grant Harley is the dendrochronologist that I work with. So when we dove the site, we brought him a whole lot of wood. And what Grant has done is gone in and taken some of these pieces of wood and has cross-dated. Now if you look over on the right, you notice really tiny rings in this fall cypress. So, but again, there's a barcode there, and using dendrochronology, we can match those variations with each other. So again, new data, nobody's really seen it. I said planted too. Okay, so not published yet. But Grant was able to get 10 pieces of wood that we brought up. Well, none of these are big cross sections of the wood. So they're just whatever pieces I could pick up off the bottom. He was able to cross-date 10 of these. What's interesting, and these are all pieces that have bark, so we know that that's when this wood died. All 10 pieces of wood cross day and end at the same time. So looking at this, so the outer gate is over here on the right. So going backwards, you can see it growing. And all of a sudden, it was these what we call suppression events, where growth increases. Then it increases again, and it's a really huge suppression event. Then there's a release, and it grows a little more, and then the trees are swallowed up. So again, really preliminary results at this point, but we're really excited about this, because this could be all due to sea level rise and saltwater inundation. So one of the things I'm trying to get Clay to do is go out and find these bald cypress that have recently died from saltwater, so we can look and see what those patterns are. So we can do a modern analog with our bald cypress forest. So another thing we did is take sediment cores, and in these sediment cores we have lots of mud, so we have pollen in there. So we can go in and identify what kind of pollen we see that's in the same layers as our wood. Okay, so we see bald cypress, we see pine, we see tupelo. So if we were to go to a modern swamp in Louisiana, we see these same species, tupelo, bald cypress. So it's very similar to what we see today on the Gulf Coast. This is where the paradox comes in. So the map on the left, this is a biogeography map, where we're looking at elevation changes on land, sea level changes in the ocean. So that pink line is sea level at last glacial maximum. The hashed part is where bald cypress occurs today. So if you drop sea level, you can imagine all the bald cypress shifting into the ocean. All the blue dots are pollen studies. All of these pollen studies, they say that during the last glacial maximum, during the ice ages, that the southeast U.S. was cold. So that's what the two diagrams are from the right. This is from a textbook. So this is what everybody assumes is correct. And that is, during the ice age, we had cold-loving trees down the Gulf Coast. And this is observed, and that observation is coming from these pollen records. So as I mentioned this morning, one of the problems with pollen is the wind blows it around, water transports. Okay. My site, I have the logs sitting in growth condition. I know those bald cypress were there. That pollen did not come from someplace. So again, that's one of the things we're really excited about in this study. This is going to kind of turn on its head what we know about the ice ages and vegetation, because cold-loving trees that everybody says is down here in the southern U.S., we're not seeing evidence of that. So we're going to go in and try to look at what's happening with the ecosystems during glacial ages, what happens with sea level rise, lots of interesting things with your life. And I'll pause there